All right, we're back. We're going to look at another Sketchpad presentation of one of your textbooks problems involving optimization, in this case, a minimum. So what we're doing here is we're trying to find, okay, this is one of the textbooks problems again, I think it's number 8. All right, so with this rectangle, which is free to resize in infinitely many dimensions, okay, we're trying to find, with the rectangle, the constraints being the perimeter is of the rectangle is 12. We're trying to find the dimensions of the diagonal, which are going to be as short as possible. So, okay, when I drag on this, I'm noting, of course, um, a couple things. Note that the perimeter never changes. The perimeter is always 12. It never changes. Um, but the perimeter is determined by the lengths AB, which we're calling X, and BC, which we're calling Y. So they're the length and the width. So they're going to be subject to change. Uh, but of course, twice their sum, which is always going to be 12. You can check on that for yourself if you need to. Okay, and of course the length of the diagonal, which is AC, is changing as well. And what we want to do is we want to see when is that diagonal going to be as small as possible. Seems like we just overshot it right here. Okay, right about there. So then the question is, what are the dimensions of this rectangle for which the diagonal is going to be as small as possible? So we've illustrated this step 1, pulling on that and watching the dimensions change. What is the relationship that expresses the diagonal in terms of x and y? So, well, that is going to be Pythagoras, okay? And so we're going to have to express that y in terms of x and find a method to determine this shortest diagonal. So let's go and investigate how we're going to do that, okay? So again, I've just captured this here, and we're going to come down and write on it. So we're going to call ABX and BCY, okay? And we should agree that twice x plus twice y is the perimeter, which is 12, which says that x plus y is equal to 6, right? Or if we want, which we will want to do, y is equal to 6 minus x. So we have to, we've taken care of this. No, we haven't taken care of this. What is the relationship and the diagonal on x and y? Well, the relationship is Pythagorean, because x and y, xy, will always be at right angles, and so therefore a right triangle is always going to be formed. And if we call this D for our diagonal, then of course we should agree that x squared plus y squared is equal to the diagonal square. That's, of course, by Pythagoras. So diagonal is therefore equal to the square root of x squared plus y squared. All right? Now, so that takes care of number 2, where we've taken the relationship that expresses the diagonal in terms of x and y, but we want to express y in terms of x, which we will bring now this issue of y equals 6 minus x. So we need a function for the diagonal in terms of x, a function for the diagonal in terms of x, which means we need to replace this y with the name established up here of 6 minus x. So we've got x squared plus 6 minus x, the quantity squared, and that, of course, is a quadratic underneath a radical, which makes it quasi-quadratic. Let's expand this out. X squared plus, this of course is going to give me 36 minus 12x plus x squared, which now becomes 2x squared minus 12x plus 36. So this is the diagonal function as a function of x. Underneath the radical is a quadratic. Therefore, making this problem, this exercise, a quasi-quadratic. Quadratic or quasi-quadratic always can apply x equals negative b over 2a. You get a lot of mileage out of that, whether it's quadratic or quasi-quadratic. And again, the quasi implying that is a part of it is quadratic, namely that part underneath the radical. And so that being the case, we can work with that component to find the minimum value of x. We should note we do have a minimum because here's our a value, which is causing our parabola to open upward, giving us a low point. All right. So negative b over 2a, of course, is 12 over 4, which is simply enough 3. So the x value of 3 is the minimum. Okay. What is the minimum? Okay, or what are the dimensions? You might be asking one and the same question. So, well, up here we said that y is 6 minus x, so then y is, of course, the same. Y is 3. So the dimensions are 3 by 3. If we throw 3 back into the function, okay, we should find the minimum distance. Okay, so that's 2 times 9 minus 36 plus 36. Radical 18, which of course is 3 root 2, which should sound familiar. Okay, like, so this is a 45, 45, 90 triangle that's formed in there. So that's the minimal diagonal length of 3 root 2 obtained when the dimensions of the rectangle are 3 by 3, which in terms is a square. Okay, so hopefully that explains that problem a little bit better for you. Okay.